Hey, what's going on, guys? So here we have a bunch of series problems right here. So here I'm going to show you how can we approach these questions, like which series test method we can use and how to identify those things. And let's go one by one, right? So let's look at the first question right here. So we have this one, n square minus 1 over n square plus 1. And if you look at this one, if you take the limit, this is going to be just 1 because we have equal powers. So the first thing for this kind of, if you see anything with summation and equal powers, the first thing we can do is we can use the test for divergence. So if you use the test for divergence, so it says like when you take the limit, n approaches infinity, and if it's not equal to 0, that series diverges. So here, if you take the limits for limits for divergence, you will get limit is equal to 1. So this one equal to diverges. So if you find divergence, you don't have to do anything else, right? So here you have to do limits test for divergence, and this is the way to approach these kind of questions. So if you find that one out, you will see this one diverges. And let's look at the next one. So here we have 1 over n square plus n. And if you notice, this is, if you take this part alone, and see, this one is a convergent P series because the power is greater than 1. So this is a convergent P series, and if you see something like this, the first thing we can do is limit comparison test. So limit comparison test says if you take the limit, like if you take this part alone, and if you divide this one by original part, and if you get a positive finite number, both of them behave in the same way. So that's the way we can approach this question. And let's look at the next question. We have this one, negative 1 power n, and these things, right? And whenever you see negative 1 power n, something like that, the first thing we recognize is this is an alternating series. And we know that whenever we have alternating series, we take the limit. We have to show that if limit is 0 and if it's a decreasing function, this is a convergent series. So you can check this one out. I believe this one converges. You can check this one out. It's converges, and this also converges. Let's look at the next one. We have sigma, these things, and if you notice that this is a geometric series. If you have n power a number, that is a P series, and if you have number power n, that's a geometric series. And you can separate these two things alone. Like you can separate these things alone, and you can show that this is, you can combine these together, and if you get a value that's less than 1, or like less than negative 1 to 1, it goes from negative 1 to 1, right? If you have R value that is between these, it means this one converges. It should be like, it's actually other way around. So this one should be bigger than negative 1 and smaller than positive 1. And if you get values between this one converges, otherwise it diverges. And you can check this one out, and if you check, so this one gives you convergent. You will get a value below between this one, so it will converges. Now let's look at this one, and whenever you see power n, the first thing is root test. First thing comes to mind is root test. So for this kind of question, we use the root test. And let's look at the next one. We have k is equal to 1 to infinity and k plus 5 power k. And here you can see this is infinity. If you take the limit, this is going to be infinity over infinity, right? So here you can use L'Hopital rule, or you can use the integral test. And if you do that, you will see this one is a convergent series. And let's look at this one. And if you notice, we have the derivative on top and ln n in the square root. So you first of all you can see there's a u substitution right here, right? Ln n is here and we have the derivative outside. So for this, if you see this kind of things with derivative like the u substitution possible, you can go and do integral test. So here we can use integral test, and if you do that you will get divergent series. And again this one right here, this is 2 power k, k factorial, and whenever you see factorials, the first thing you have to do is you have to take the ratio test, because if you do the ratio test you can cancel these factorials out, you can get rid of these factorials out, and that will make everything easier, right? So this thing we do ratio test, and if you do that for this one, that's gonna give you a convergent series. Now let's look at this one. Again we have, if you notice this 1 over n here, the derivative is on top. So here we can do the u substitution. Here u substitution is possible, so we can do the integration test for this one. Integral test, or you can see that as the n increases, this value becomes smaller, right? And if you notice that we have a convergent p series because we have e over n square, and if you take 1 over n square, this is a convergent p series. So you can also do direct comparison test. Direct comparison, and let's look at the next one. We have tan inverse n and n. So again we have in the denominator we have n power 3 by 2, and we have tan inverse n, and if you remember, tan is bounded by 5 by 2 to negative 5 by 2, right? You can compare this value and you can do the direct comparison because we have p series in the denominator, and you can take the next value and compare your series. And this one converges, this one 9 is convergent series, and this one, if you check this one out, this is also a convergent series. Now let's look at this one right here. We have sine 1 over n over square root of n, and here the bn value is going to be 1 over n power 3 by 2. You can see, you may ask, how did I get 3 by 2? That's a long process. If you try this one out, you will see there's a limit that says if you have sine function and if you have the same value in the denominator, you will get, the limit is going to be 1. So that's the approach for this one. So for this one we take direct comparison again, and this is, if you try this one out, this is a convergent series. And let's look at this one right here. We have k 1 to infinity, 3 power k. So again we have infinity over infinity. So here we can use L'Hopital rule, and then also you can see test for divergence, and if you check this one out, you will see this one diverges, right? So you can check direct test for divergence also. Test for divergence. So when I see this, I remember for this one also, like for this kind of, if you have an exponential function, you can use ratio test too, right? So whenever you have exponential function, you can use ratio test. And the next one we have here is k square times e power minus k. So here we can use integration test, and this one is going to be integration by parts, right? Integration test, integration by parts, and if you do that, you will see this one converges. And let's look at this one, and here again we can look at this part. If you see n square, if you take this one n square over n cubes out, that's going to be 1 over n. That's a divergent p series. That's a divergent p series, right? 1 over n, that's a divergent p series. And here you can use limit comparison test. And if you do the limit comparison test, you will get this series also divergent. Or if you can show that in direct comparison, if you can show that 1 over n is smaller than this one, you can do the direct comparison too. So limit, both of them are possible. Limit comparison and direct comparison. So in order to do direct comparison, if it's a divergent series, we have to have a series that is this, like whatever the value getting from the dominant values. For example, for this one, 1 over n, right? If the dominant value converges, and if you can show this one is bigger than this dominant values, you can do direct comparison test. If it doesn't work, then you have to go for the limit comparison. So here, for this one, direct comparison works. And if you find this one out, you will see this series actually divergent. And that's how we can approach these kind of problems. I hope you guys find this video helpful. See you next time.